Hi everyone, in today's video I would like to go over an example that I saw from Google Cloud, which is quite interesting because it provides a template that you can use to deploy any generative AI application on the cloud with a production ready setup so that you can move beyond proof of concepts and really have GenAI apps that can scale to lots of users. And this example is quite nice, I think, because it's also quite similar to how we also set up GenAI apps at ML6. So my goal of this video is basically to go through this GitHub repository over here, go through the code, set it up ourselves on the cloud, and then we can basically start seeing how we can scale GenAI apps to millions of users. So if we walk through the README over here, you will see that quite a lot of services are of course used because this is a Google Cloud example, so a lot of GCP services will be used. And so they do provide two different flavors of the deployment. So for one they use Cloud Run, and for the other one they use GKE. So GKE is short for Google Kubernetes Engine. Kubernetes is like a technology that is used by a lot of companies if they want to scale an application to millions of users. So Kubernetes is what is called a orchestration service. And it heavily relies on containerized apps, and so for that, Docker is typically used. So if you want to deploy something to production, for example a GenAI app, but it could also be just a web application, then Docker is something that is very often used. So what is Docker? Basically, Docker is some kind of isolated virtual environment, virtual operating system that allows you to run something on every possible device that has Docker installed. So if you, for example, implement an app on your MacBook, then you can containerize it, turn it into a Docker container, and then anyone else who has Docker installed on their device, could be a Windows laptop, could be a Linux system, if they also have Docker installed, then it allows them to also run your app. So it's basically allowing to ship applications to other devices so that everyone can just run it. There's a whole technology behind the scenes regarding how Docker works. I just know how to create Docker containers, so how to turn an app into a Docker container and then run it. And this is something that also the cloud providers like Google Cloud, Amazon with AWS and Azure heavily build upon. So every time you want to, for example, productionize an application, you always first need to turn it into a Docker container, then deploy it on the cloud environment, and then technologies like Kubernetes are used to then automatically basically scale those containers. So by scaling we mean that, for example, it might be that your application receives more and more demand from people using your app. So then Kubernetes is the service that will allow your app to automatically scale to the to more users. So this is all handled by the cloud for you. This is all handled by Kubernetes. So this is available on any cloud platform. So on Google Cloud you have GKE, Google Kubernetes Engine, but Kubernetes itself I think is open source and is originally developed by Google. So they call it production grade container scheduling and management. So basically once you have such a Docker container, the Kubernetes allows you to automatically schedule them, manage them, and basically allow them to scale. So they will basically provision more and more containers whenever your application gets more demand, and when demand gets lower, then the amount of containers also gets lowered. And so for this example app, you can either deploy your whole app on GKE, so on Google Kubernetes Engine, but they also have something a bit more high level, which is called Cloud Run. And this is a service that I really like on Google Cloud. So Cloud Run is similar to Kubernetes, so it also relies heavily on Docker containers. So whenever you have some generative AI app, for example, you need to first turn it into a Docker container. Then you need to push that Docker container to what is called an artifact registry. So this is like just a hub of all kinds of Docker containers. And then you can deploy it either on Google Kubernetes Engine or on Cloud Run. Cloud Run is more high level compared to Google Kubernetes Engine. Kubernetes itself, yeah, still quite low level, like you still need to implement quite a bunch of files yourself, making sure that the deployment runs smoothly. Whereas Cloud Run is more high level, they handle more for you. You can just say, hey, I want to deploy this Docker container on the cloud. Please do that for me. And Cloud Run is what we call a serverless service. So by serverless, we mean that Google will handle the servers for you. You don't need to take care of hosting those Docker containers, and you only get billed for the amount of time that the Docker container is running. So every time there is some demand, then Cloud Run will spin up, handle the request for you, potentially scale to more containers if required, and then when there's no demand, for example, it can also scale to 0. So it means that you're not provisioning anything, you're also not paying anything. So this is why Cloud Run is pretty nice, because it allows you to only pay for what you use. So only when your app is actually up and running, when there is demand for your application, you will be billed. Whereas Kubernetes Engine, which I assume Cloud Run is using behind the scenes, is more low level. And there, things like scaling down to 0 is harder to implement, because there you typically provision like a virtual machine instance to what is called a Kubernetes cluster. I'm gonna go further into detail regarding what that means in a bit, but it's more low level, and there you typically get billed per hour that a virtual machine, like an actual computer, is running. Whereas here it's fully serverless, which means that you only pay for when the containers are spinned up, and you're not billed when nothing is running. So this is just, of course, explained for Google Cloud, because on AWS, for example, there are different services. Like there's AWS Lambda, which is a popular service if you want to deploy a serverless function. So this is also similar, like it will only spin up when there's demand, then process something for you, and then it will automatically scale down as well. So you're only billed for the actual compute when it's running. And then on Azure there is something similar. It's called Container Apps. Azure Container Apps, which is also a fully managed serverless container service. So also there, if you have some Docker container, I will explain a bit how you can turn your generative AI application into such a container. With Azure Container Apps, it will also only run when you actually have demand for your application. So here, so they say deploy a production-ready generative AI app in less than 30 minutes. So you can either choose to use the more level Google Kubernetes Engine or the more high-level Cloud Run service. So I would recommend to start with Cloud Run. We'll go into details. And then they use some other services like Cloud SQL, Vertex AI, and PG Vector. So the application that we're going to build here is a typical what is called a RAG app. So RAG is short for Retrieval Augmented Generation, and this is a very popular use case, I would say, with generative AI models like ChatGPT and so on. So the idea is basically to have models like ChatGPT be able to connect with your data. Every company has their own data sets, their own knowledge, all stored in textual form or PDFs, for example. And so a RAG application allows you to chat with your domain-specific data. So the idea is very simple. Whenever you have some question regarding your data set, let's say you have a company and they have a lot of internal textual documents regarding, for example, the policy of holidays, like when employees want to ask for a holiday, how is that done? They also have, for example, policy when you're sick, and what is the process that you need to fulfill if you want to ask for holidays if you're sick. And then let's say you also have an IT department within the company, and they also have all kinds of documentation regarding IT problems that you might encounter, and you want to get help with that. Well, you could just collect all those textual information and store them in a database, and then whenever someone wants to chat with ChatGPT and just ask a question like, hey, I want to ask for new holidays, how can I do that? What is going to happen is we're going to first retrieve the most relevant documents from that database, from all the textual documents that the company has regarding holidays, regarding IT problems and so on. And then based on that question, we're going to retrieve the most relevant documents. So this could be like the top 5 or top 10 most relevant documents given the question of the user. And then we're going to provide those as context to our large language model like ChatGPT. And then the LLM will basically get your question as well as the most relevant retrieved documents as context, and then it will provide a response in natural language. So yeah, this is the ID. So it's pretty simple. You just retrieve the most relevant documents first from a textual database, and then you are going to provide those as additional context to your LLM. And so for that, you of course need to store all your documents in some kind of database. And so for that, this application recommends to use CloudSQL. So CloudSQL is a relational database that you can use on Google Cloud. So they do support different flavors of such SQL databases like PostGreSQL, MySQL, SQL Server, and so on. And in this case, I think we're going to go for Postgres. So that's where the vector database comes in. So basically, we will allow users to send a question to the generative AI application, which will first going to retrieve the most relevant documents within that what is called a vector database, because we also are going to need to store vectors besides the textual documents in our database, because the retrieval is done based on vector similarity. And then finally, we are also going to then, once we have retrieved the most relevant documents, we're going to provide those to a large language model, which in the case of Google Cloud could be the Gemini LLM. So Gemini is one of the, it's actually the large language model family that Google provides. If you're on Google Cloud, Gemini is probably a good option. But you could of course also go for other large language models, like the ones from OpenAI, the ones from Anthropic, or you can also go for an open source large language model from Hugging Face, for example. But I assume in this tutorial they are going to use Gemini. And so once the LLM has received both the question and the most relevant documents, it can then send a response back to the user. So that's the basic idea of this simple generative AI application. And as you can see also, they are going to deploy everything in what is called a VPC, or virtual private cloud. So this is mainly for security reasons. Basically, those 3 things over here are going to communicate with each other within a virtual private network to ensure that nobody else externally can just access those services right away. So this is just an important security aspect if you're deploying such a generative AI app on the cloud. So as I said earlier, they have 2 flavors. So here, as you can see, the generative AI app will be deployed on Cloud Run, serverless service. Alternatively, you could also deploy it on Google Kubernetes Engine. So they do provide 2 folders here, one for Cloud Run, one for GKE. I'm gonna start here with Cloud Run. And we can just go through the code and see how everything is implemented. So I also set up a cloud project for this specific use case. So let's see, I called it experimentation. All right, so we are already, so that's the first thing actually you need to do. You need to go to console.cloud.google.com, which is the main interface to interact with Google Cloud. And there you need to create a new project and also set up billing. So you need to provide your MasterCard or any other financial card to it, so that you can also get billed. But trust me, we're not gonna spend a lot of money, especially since most of the services we're gonna use are serverless, which means we're only paying for them if there's actually demand for them. But then once you have that, you get a certain project number and a certain project ID, and you need those if you then want to interact programmatically with the cloud project. So let's just dive into this a bit and see how you can set up something like this yourself. So as you can see, they first require you to install gcloud, so that's something I have already done. So if you go to your terminal, I can, for example, see that I have gcloud already installed, but for that you would need to follow this guide and then install it on your specific device. So this will allow you to programmatically interact with Google Cloud. So from the terminal you will be able to, for example, set up infrastructure on your cloud project. So that's the first thing you need, and then the second thing you need is Terraform. So what is Terraform? This is also something that I learned from deploying things on the cloud. So Terraform is what we call infrastructure as code. So basically Terraform will allow us to specify all the services that we want to set up on our cloud project just via code. So we are gonna be able to just specify everything via code. So you can see that already here in the Terraform folder. So here, as you can see, so it has this .tf extension, which is short for Terraform. For example, if you want to set up a network, you can just do that via code in Terraform. So here, they have all kinds of modules which allow you, and then resources, which are the actual resources that you set up on the cloud project. And the reason that Terraform is very easy is because otherwise you would have to go to the UI, then, for example, go to network, and then do everything via the UI. So you would have to first we need to enable some APIs, and then you can click here on create network. For some reason I'm not able to load this, but everything could of course also be done just through the UI, but that's not really scalable, because if you want to set up, as you can see, lots of services, and also typically if you're setting up such a project, you typically have a dev project, you create a project just for development purposes where you already set up everything, but you do it just for testing purposes for yourself, for the developers. And then you typically also have a second project which can be called the test project, where you, for example, already have some users testing the application. So there you can then use Terraform to just set up the exact same infrastructure using code, whereas if you had to do everything through the UI, that would be of course a huge amount of work. And then finally you also have a typical third project on the cloud, which is then the production project, where you can again run Terraform to deploy all these services. So Terraform just allows you to set up infrastructure way faster and makes it much more scalable compared to do everything through the UI. So this is why Terraform is very useful. And so you also need to install it, of course, on your device. So let me check that. But what I use for that actually is tfenv. So this is just a version manager for Terraform. It's very handy because it allows you to very easily install different versions of Terraform. You can say tfenv install, for example, I want this version of Terraform, or I just want the latest version of Terraform, and it allows you to just switch between different versions of Terraform, because one project may be using Terraform 0.3 and the other one might be using 1.0. So with tfenv you can easily switch between them. Then they suggest to set up some aliases in your terminal, that you can just say tf instead of having to type Terraform. I'm not doing that. And then here, as you can see, you can start logging in to your project, so we can do that. So the first thing I'm going to do here is I'm going to create a new folder, or maybe I can, for ease of use, maybe just fork this repository. So what you can do is you go to this link and fork it. So forking means that you create a copy of the whole repository for yourself. And then I'm gonna clone it. So by cloning, we mean that we're gonna bring it to our own computer. So git clone and then the URL. And then I can move to that folder. So it's Cloud SQL. Cloud SQL. Alright. And then I'm gonna open that up in Cursor. Yeah, I'm using Cursor as the IDE, but feel free to use VS Code or PyCharm if you're using a different one. Alright, so let's follow the README over here, not the GKE one, but the Cloud Run one. Alright, so yeah, the first thing we need to do is like authenticate with our cloud project. So you can do gcloud out login, and this will automatically open up a browser. And then you can log in with your account. Click a bunch of allows, and now we are authenticated. But you can also type gcloud config list, I think. And then, as you can see, I'm still using another project, which is not what I want. I want to do gcloud config set project, and then the project ID that we just set up. So for that, let me go back to the... So here I need the... something that confuses me is, do I need the project number or the project ID? It seems that we need the project ID. So I'm gonna copy that. And now if I run gcloud config list, as you can see, we now seem to be able to... another thing I need to do is gcloud out application default login. That's another authentication that I typically also have to do when I want to make sure I'm authenticated with the cloud project. Okay, but now we are fully authenticated with our cloud project. So let me go back to the README, because we're gonna follow all the steps needed. So yeah, the first thing they're gonna do is bootstrap Terraform using the Terraform bootstrap folder. So this is this folder over here. So there, as you can see, there are just 4 files defined for Terraform. There's a main.tf. So what is going to happen here is they're going to create a cloud storage bucket. So what is a cloud storage bucket? It's like, just a very simple place where you can store some data. Could be any kind of data. Typically blob data is stored there. So blobs could be anything like videos, images, text files, and so on. So, but the reason we have this Terraform bootstrap folder is because Terraform makes use of what is called a Terraform state. So a Terraform state is basically, a file that keeps track of what are all the services that are currently already set up on your cloud project. Because Terraform needs to sync with that. If you're running Terraform locally on your own computer, Terraform needs to know which services are already set up and which ones aren't. Because if you're then gonna run Terraform locally, you're gonna create additional resources or remove others. So that needs to be synced between your own laptop and the cloud project. So for that, what is done here is we're gonna create a storage bucket. So it's just a place to store the Terraform state. So as you can see here, they give as name some random ID first, then bucket, and then Terraform state. So this is where they're gonna store that state of Terraform, just to make sure that we are always synced and make sure that Terraform on our own computer knows which services do we already have set up on our cloud project and which ones that we haven't. So this is a resource that they enable, and then they also enable some APIs on the cloud project. So for example, we will need Cloud Run. Like if I would go here to Cloud Run, it will probably first ask me or prompt me to say, hey, you need to enable that API. Okay, in this case I seem to be able to just use it right away, but maybe I think for Kubernetes engine it might be that they first ask you to enable that API. But so this is all done programmatically here as well, because these are all the services that we were gonna need. Like we're gonna need cloud storage to store like the bucket and this Terraform state within that bucket. We need the secret manager, which allows you to store passwords and API keys and so on. So these are all the services that are needed. So Terraform has some specific format, some specific syntax, like locals are just local variables that you define. It's called service list here, so it's defined in a service list. And then here we're gonna create all these services using the Google Project Service resource. So you can always Google all these resources. Like if you just search for the name of the resource and then Terraform, then you can find all the documentation on the website of Terraform. So for example, this one allows management of a single API service for Google Cloud Project. So these are all the services that we are providing to that resource. And then you also specify, as you can see here, the name of the project. So as you can see, Terraform uses the var dot name of the variable, and then here each dot key will provide each of those services to that service, to that Google Project Service resource. So as you can see here, we specify the name of the project as a variable. So that's defined here. So we have two variables over here. So the name of the project, it will be again the project ID, and then the default region. Typically, when I deploy a project on Google Cloud, I don't use the US Central 1 region, but rather I use the Europe West 1 region, which is a data center by Google in Belgium, which is also the country where I reside. Because for the client project that we do, we also often require that all the resources within the cloud project are deployed in Europe for GDPR reasons. Then this is just the Terraform provider. So there are different providers for deploying Google services on Google Cloud using Terraform. But as you can see, like this Terraform Bootstrap folder doesn't do a lot. It will just create, it will enable all these services, and it will also create that storage bucket to store the Terraform state. And so that's the first thing that the README here is describing that you need to do. Bootstrap Terraform using the Terraform Bootstrap folder. So for that, as you can see, they say first change into the Terraform Bootstrap directory. So that's the first thing we have to do. So for that you can do cd, and first need to go to the run folder and then to the Terraform Bootstrap folder. Okay, so then we are in that folder. And then they say create a file named tf. These are like the actual then values of those variables. So if you go here to Terraform Bootstrap, I can create that file, and this is going to store the actual values of the variables that are then being passed to that variables.tf file. That's just how Terraform works. So here, for example, the Google Cloud Project, there we have to specify the project ID. So let's go back to our cloud project, and then here I need the project ID, so I'm gonna provide that here, and then here for the default region I'm gonna choose Europe West 1. So only those two variables need to be set in a .tfvars file, and then Terraform is gonna automatically supply those to this variables file over here, and this is again then passed to here where you have var.Google Cloud Project and so on. So that's just how Terraform works. Okay, so the project name should be an existing project. The region should be the region you want to deploy your infrastructure in. So we have specified Europe West 1 in our case. And then they say run the following to see what changes will be made. Terraform init and then Terraform plan. So the way Terraform works is also like, first you need to initialize Terraform. So for that we have to run Terraform init. But it says that there is no such file or directory. They are probably using. There might be an issue with my tf. There seems to be an issue with my installation of Terraform. So I'm gonna first fix that. So for that, let's go back to tfenv, because that's something that I have already installed. Yes, okay. And then here normally you can do tf install and then a specific version. So I'm gonna try to do tf install tfenv. Okay, so they say Terraform version 1.11.3 is already installed. But when I do that, so one thing you can do to like quickly debug things is just ask it to Claude Sonnet 3.7, which is currently one of the best models for coding alongside Gemini 2.5 Pro. I see you're having an issue with the tfenv, the error message. Okay, try running this. Let me try that. Yes, now we seem to be able to use Terraform correctly. That's weird. So let me try that again. Yeah, now it works. So yeah, the thing we had to do is also switch to that version that we installed apparently. So now we have successfully initialized Terraform. Great. So now you can move on to the next phase. So yeah, Terraform has like this distinction between planning something and then applying something. So because yeah, just creating resources on a cloud project, it can destroy a lot of things for you. Of course, you don't want to break your existing projects. You don't want to remove or destroy resources or create new ones without intention. So this is why you can always run Terraform plan first to see what Terraform is going to plan to create for you. And then you can run Terraform apply to actually apply those changes. So in this case, as you can see, it creates or plans to create 13 different resources, 0 to change and 0 to destroy. So it's only gonna add stuff, which is great because I'm just gonna double check that we're properly logged in, but that seems to be correct. So then once you say okay, the plan is okay, looks okay, then you can run Terraform apply. So now let's do that. Terraform apply. So it says, yeah, I'm gonna add 13 resources like the storage bucket and so on, all the services that are gonna be enabled, and it's gonna change or destroy nothing. So then you have to type manually yes, and then it starts creating all those resources for you. Let me just check here. Okay, all seems correct. So now it's creating those resources. So it's gonna, but note that this is just some resources that we create to manage the state of Terraform itself, like the storage bucket, and then enabling those services. We're not creating the vector database, the Cloud Run app, or the embedding models yet. That's done in the actual Terraform folder. So that's the next step. So let me just wait here. Okay, so that seems to be already enabled. So now it has added those, so you can actually check that if you now go to your cloud project. And let's go to the storage buckets. It should have created our bucket to store the Terraform state. So that's done over here. Great. Nothing seems to be added there yet, but it has created the Terraform state bucket, which is nice. So that's the first thing we had to do. Okay, and then for the rest of this guide, we'll assume that you're running Terraform plan before Terraform apply to ensure the changes match what you expect. Otherwise, we will omit the planning step for you. Yeah, makes sense. Okay, and then yeah, you can also run Terraform output to get. This is another thing that Terraform has. It's like outputs. So if you go here to your main.terraform file, you can see that an output is being defined here. So then afterwards you can run Terraform output to see the value of what you define as an output. So in our case, we defined the name of the bucket as an output. So this allows you to see the name of your bucket. Save this for the next step, where we will tell the main Terraform deployment where to save the state. Yeah, we need this. Probably we're gonna have to provide that. Yeah. So then the next step, so once we have set up our storage bucket where we're going to store the Terraform state, we can move on to actually creating the whole infrastructure for our application. So now with a storage bucket ready, we can move on to the Terraform directory and create all the infrastructure. First, you need to configure Terraform. First, create a backend.conf file, updating the bucket name to your... So I assume that we need to do that within the Terraform folder. So let me go to that folder, Terraform, and then here they say now it is, yeah, we can move on to the Terraform folder. Yeah, so create a backend.conf file. So I'm gonna do that like this. It seems to be ignored by Git by default, and then you can specify the name of the bucket together with a prefix. So now we have to provide the name of that bucket. So that's this one. So I'm gonna copy that over and paste it over here. Okay, so that's done as well. And then you have to run this specific command. Well, we have to run Terraform instead of tf, the alias that they defined. Okay, so that's again to initialize Terraform and make sure that the state is going to be stored within that bucket. But so as I said, like now we're actually going to create all the resources that we need for this specific project. So for that, let's move into the Terraform folder, because as you can see, quite a bunch of resources are being created here. So let's go over them. The first one is an artifact registry. So I already talked a bit about this. So what is an artifact registry? It's like it used to be called container registry on Google Cloud, but now they are deprecating container registry, and people need to move on to use artifact registry. So it's literally a hub of containers, like a collection of Docker containers. So whenever you have some Docker image, you can just push it. Well, yeah, I have to say a Docker image and not a Docker container, because a Docker container is actually a runnable instance of a image. But so it's a collection of Docker files, as you could say. So as you can see here, they create that. So again, if you want to look up the documentation for how to create a artifact registry on Google Cloud using Terraform, you can just Google it as in this way, and then as you can see, it's a repository for storing artifacts like Docker images. Again, they provide some variables to it, like the name of the Google Cloud project, the region, the name of the repository, because artifact registry consists of repositories in which you can then push your artifacts, description and format. As you can see, Docker is being specified here. So that's one of the things it will create. Why do we need that? Because we're gonna deploy our app. We're gonna create a Docker file for that, then we're gonna push it to artifact registry, and then Cloud Run is gonna use the Docker image from artifact registry. But I will explain that in a bit. So let's go back here, and then next it creates this backend file. But yeah, this is just specifying that Google Cloud Storage seems to be used as backend, so that probably specifies to Terraform that it can store its state within a cloud storage bucket. Then here the database is created. So yeah, so in this case they use a Cloud SQL instance as the vector database. There are actually different options for creating a vector database. Like there is Elasticsearch, which is a popular vector database to store data, like textual data, and then also the vectors that you need for retrieval. Other examples are Weaviate, which is another popular vector database. There is Pinecone, and so on. There are many more. People are even also using MongoDB, and so on. But in this case, Google is gonna recommend to use Cloud SQL. I will also go maybe in a different video explaining why they recommend to use Cloud SQL. Because, okay, let me quickly explain why. So this is based on this blog post over here. Vector databases are the wrong abstraction, because there are so many vector database vendors out there. Like there's Chroma, which is another one. There's Quadrant, there's Pinecone, as I said earlier, and so on. The problem is, for all these kind of new generative AI applications, people set up a separate vector database, which then stores all your textual documents, all the internal wikis that companies may have regarding all the information they have. And then you also store the corresponding vectors, so that you can then retrieve the most relevant textual documents based on vector similarity. But as this blog post argues, is they say that most companies already have stored their data in some kind of SQL database, some kind of transactional relational database. So they say they don't recommend to then set up a second vector database where you're only going to store your vectors. Instead, they recommend to just add your embeddings as a separate table into your existing SQL database. So that's shown over here. So let's say you already, most companies might have already such a SQL database. So they say rather than having to create a new separate standalone vector database, could be Pinecone, Weaviate, Elasticsearch, and so on, Quadrant, Chroma. There are so many. Rather than doing that and having to then sync between those two different databases, why not just add a embeddings table to your existing SQL database where you already store your data anyway? Because this will allow you to not having to do this synchronization all the time between your embeddings, your vector database, and your SQL database. And so, yeah, this whole blog post argues that most companies don't need to set up a separate vector database, and instead they can just add their embeddings as a table within a SQL database, so that you don't need to sync and maintain two separate databases. But yeah, I might have to create a separate video just to describe this whole idea. But in this case, actually, yeah, you could view it as a similar view as the blog post. So they are going to use Cloud SQL, where companies might already store a lot of their data anyway, and we're going to store these vectors in that database itself, so we don't require to maintain and synchronize two separate databases. So this is why if you go here to the Terraform folder, the database is a Cloud SQL instance. So for that they create that over here, all done programmatically using Terraform. Lots of arguments are being provided here. So as you can see, you can then also specify the hardware that you're going to use to deploy your Cloud SQL instance. So they use a machine here with 8 CPUs and 64 gigabytes of RAM. They provide 250 gigabytes of disk size. So again, you could find all the documentation on Terraform's website. And then here, yeah, you can also find like all the documentation regarding all the arguments that you can provide. Like if you're, for example, interested in seeing like the disk size, for example, how to provide that. Here you can see the documentation. So the size of the data disk in gigabytes, the size of a running instance cannot be reduced but can only be increased, and the minimum value is 10 gigabytes. Okay, so that's created here, and then they also create a user for that database. Yeah, another thing which I probably will have to explain in this video as well is like service accounts, because another very important thing if you're working on a cloud project is like authentication and security, and making sure that resources or people can access the resources that they are allowed to access, and the whole access management thing is quite an important topic if you're working on a cloud project. Oftentimes I'm actually more working on setting up authentication and service accounts rather than with the main logic of my application. That's kind of a little frustration when I have to work on the cloud, but of course, yeah, security and privacy is really important. So yeah, here they set up a service account which will basically allow a certain user to then access that database. And it seems that the database is going to be called retail, so we're going to store some retail data in that database. So as you can see, we have to create both a database resource and a database instance. So that's new for me. I didn't know there is a difference. So here, but yeah, anyway, that's how the database is set up. Then as you can see here, we create, so IAM is like all the access management on your cloud project. So if you go back to our cloud project and you type in IAM, so this defines like this whole access management thing, where you basically define, for example, here we have 2 people, and then we will, for example, specify, okay, Niels is able to access this and this resource. And then a service account is kind of a thing that you use for services on Google Cloud, and then you specify this service can access those other resources. So for that, a service account is being defined. So that's, for example, defined for the Cloud Run instance. So we define a service account for Cloud Run. So basically this service account, which is gonna then end up here in the IAM settings, is gonna define which resources can this Cloud Run service then access. Like we will have to define that the Cloud Run instance over here, which is gonna use the Cloud Run service account, can access the Cloud SQL database, for example, or it can access the embedding models and the large language models, and so on. So this is why IAM is quite an important step. So as you can see, quite a bunch of service accounts are being created here, for example for the database access and so on. So as you can see, they create 2 service accounts over here, one for the Cloud Run instance and one for Cloud Build. Cloud Build is yet another service on Google Cloud, which we are going to use to basically create our Docker containers and push them to Artifact Registry, but more on that in a bit. So as you can see, we create a service account here, which will be used for Cloud Run. So it's a custom service account for the Cloud Run service. And then, as you can see, we define database access, AI platform user, and secret manager access. So it basically defines that this Cloud Run service over here will have database access, so it will be able to talk to the Cloud SQL instance. So that's defined over here. So for that, you need a specific role. So yeah, IAM on Google consists of roles, and then each role is a set of permissions. So if you would search for this role on Google Cloud, we can probably find it here. Let's see. Yeah, so this, for example, this role then gives you these 2 permissions. It gives you the cloudsql.instances.get permission and the cloudsql.instances.login permission, and so on. And then, yeah, we also define AI platform user. So what this means is that it will allow the Cloud Run app to use AI models from AI platform, which is the service for using AI models on Google Cloud. And then also secret manager access. So this is used to access passwords or API keys on Google Cloud. And then the same thing is being defined for Cloud Build, but I will explain in a bit what Cloud Build is and how we can use it. And for that, we are going to add 3 different roles: one to write logs, a storage admin role, and a artifact registry write role. So as you can see here, we are going to use Cloud Build to write our Docker image to artifact registry, which is why we need that. So this is all defined in the IAM folder. Then the main folder, the main file seems to define the name of the network. Like as I said earlier, if you go back here to our figure, this whole thing is being run in a virtual private network, or in Google is it called a VPC, or virtual private cloud. So here they specify the name of that network, and then within that virtual network you also have subnets, which are then smaller ranges, I would say, of IP addresses. I'm not a network expert, but this is another thing you need to define when you want to then deploy all your services within Google Cloud. So that's for the main file. So here the actual network is then being defined, it seems. So GCP network. Again, the project ID is being passed as a variable, and then here, as you can see, subnets, ingress rules. So yeah, for that I'm not that much of an expert, but it basically allows you to define like which IP addresses are allowed to get access to that network. For example, here you allow that there is internal traffic on that network using the TCP and UDP protocols and so on, but yeah, for that I would have to probably do another deep dive in a separate video. And then they also define a compute forwarding rule, DNS server, and so on. So yeah, I'm not going to go into the details of that, but just be aware that we're going to define a virtual network on our cloud project so that these services will be able to talk to each other, and that everything stays private. So they're only going to be able to access each other within that virtual network, but anyone externally will not be able to access it. Again, we define in outputs here, so that's something that you can then always print afterwards. In this case, we seem to be able to then get a root password for Cloud SQL instance. Again, the provider will be Google in this case, because yeah, our project is Google, so we need the Google provider for Terraform. So secrets, as you can see here, we create the secret manager, which will allow us probably to store like the passwords to access the database and so on. And then yeah, here we probably also need like an API key if you want to use the embedding model. So this is why the secret manager is being defined in Terraform. So that's defined over there. And then again, we are gonna seem to create another cloud storage bucket. So we already have one for the storing the Terraform state, but this one will be used for cloud builds, which I will explain in a bit. Okay, and then again, variables. So these are the things that it takes in as an input. Not a lot of stuff here, just the name of the project. I assume these two will have the same value. And the name of the default region. And finally, the versions of Terraform. So this is quite Terraform specific. Okay, so now I think we're ready to create this whole infrastructure on our cloud project. So we have done this, and then we have already run this as well. So again, we have to then specify the names of the variables. So I'm going to create a terraform.tfvars file over here, and then we need to provide the project ID. So for that, I'm going to go back to my project, copy over the project ID over here, like this, and specify default region. So I'm going to use Europe West 1. Okay, so that's also done. Nice. And then, okay, if you want to put your Cloud Run service and Cloud SQL instance in separate projects, use different project names, but we're not going to do that. We're going to specify and have our two services, like both the Cloud Run app and the Cloud SQL instance. We just want that on the same project. Okay, and then, yeah, as you can see here, they explain all the services that are going to be created when you run Terraform apply. Let me first run, I'm not sure whether I need to run Terraform init here as well. Oh no, it was already initialized when we were in this previous comment. Great. So then I can run Terraform plan first to see what resources, what kind of infrastructure Terraform is going to set up. So in this case, it's going to create 32 different resources on our cloud project. And it's not going to change anything and not going to destroy anything. So that's great. So then I think we're ready to actually apply Terraform. So then I can run Terraform apply, and then I can just say yes. It also says here that it's gonna provide the outputs for the Cloud SQL root password and the PSC DNS name, which we might need later on. So yeah, here they say now would be a good time to read through the various Terraform files. Once the infrastructure is done, you can look in the console to see all the various pieces. So I already went through most of the Terraform files in the Terraform folder over here. And then, yeah, we now are letting Terraform set up the whole infrastructure. And then once that's done, we can actually go back to our console and see whether it has created, for example, the artifact registry, the secret manager, and so on. So if you would go, for example, now already to secret manager, it's probably too early to already see it. Okay, it seems to already have created them. Nice, I had created them 1 minute ago. Because like we're still like just setting up all the infrastructure. So it's going to create a database on Cloud SQL. So let me go to Cloud SQL. And it seems to create this toys inventory instance. So this seems to be specified somewhere. Yeah, this is the name of the database, as you can see here, specified in Terraform. But it's still being updated, as you can see. Yeah, and so once we have set up all the infrastructure, they basically build some app images. So what is meant by that? So so basically now with Terraform we will have set up a Cloud SQL database. So it will allow us, yeah, to populate that database with some data, and then, yeah, the idea would be to have a RAG application, Retrieval Augmented Generation. So we're going to augment the generation of our large language model by first retrieving the most relevant data out of our database. And so for retrieving those most relevant documents from our database, we're going to use vectors, or also called embeddings. because the retrieval will be done based on vector similarity. And so, as you can see here, they have 3 different apps that they create and then deploy on the cloud. So the first one is Initialize the database. So this is an app that connects to the database as a super user and sets up permissions and the PG vector extension. Because to basically store vectors or embeddings within a SQL-like database, they are using PG vector. So this will basically allow us to perform that vector similarity search for Postgres kind of databases. So PG vector is open source, and you can just see here how you, for example, can create a table with an embedding column with, for example, vectors of size 3. And then you will be able to use this operator over here to then find items based on, as you can see, this operator stands for the L2 distance, but they also have other kinds of vector similarity implementations like the negative inner product, cosine distance, and so on. We're also going to see which of those are going to be used. But so PG vector is quite essential if you want to do vector similarity search within a SQL database. And so for that, let's maybe look first into the init database app. So the most important file is called main.py here, so it's defined in Python. So what we're gonna do here is basically just connect to that database. So for that, you need to use the Python client to connect with your database. So for that, the async pg library is used. So this is, as you can see, a database interface library designed specifically for PostgreSQL and Python async.io. So it basically allows you to connect with your database using Python. So you can just do pip install async pg, and then, as you can see, we connect to the database, and then they just set some privileges. As you can see, grant all privileges on the database, grant all on schema public to create extension. So this seems to be a SQL query. To grant all the permissions that are required. So as you can see, the script really doesn't do a lot. It will just connect to the database and set up some permissions, like granting some privileges on that database. So it's very, very minimal. But as you can see, so this file is just defined using Python. So it's just a main.py script. Of course, we could just run this locally on our computer. We could run python main.py, and it will connect to that database and set up those privileges. But what they are going to do here is they're going to basically deploy that Python script to our cloud project, and then we're going to execute it on the cloud. And for that, what is going to be used here is what is called Cloud Run Jobs. Cloud Run Jobs is actually also a very handy service, I would say, on Google Cloud, because it allows you to basically just execute some code on the cloud. Could be a Python script, could be something else. But it's just some code that you can execute manually, or you can also execute it based on a scheduled basis. Like, could be a cron job, which is something that is run on a regular basis, like every day, for example, or when some new data from another service comes in. So this is why they define this job.yaml file over here. But so as I said earlier, like if you have some Python scripts and you want to run it on the cloud, or if you have some other kind of code that you want to run on the cloud, you typically need to turn it into a Docker image, which is then run as a Docker container. So what I mean by that is you need to define this Docker file, as you can see, which is basically going to allow anyone that has Docker installed on their device to run this Python script. So as you can see, this is how a Docker file is defined. So you basically specify a certain Python version, then you copy over, you create a certain directory within that Docker container, and then you copy over some files. Like in this case, they copy over the requirements.txt file, which is just going to list the dependencies that we need. So as I said earlier, we need the async pg Python library with version. You can like fix the version over here, and we also need this async timeout dependency, which probably is going to be imported over here. And then so within that Docker file, we copy over that requirements.txt file, within our code folder, and then we're gonna run pip install the requirements, and then we're gonna basically also copy over our main.py script, and then here you can specify what the Docker image or container should do. So it's gonna just run python main.py, and then cloud build is gonna be used to basically push that Docker file to artifact registry, and then also run it as a cloud run job. So here, as you can see, what happens. So basically the flow is you first define your main.py script, like just the logic of your application. So in this case, connecting to a database and granting these privileges. Then second step is creating a requirements.txt file specifying what are like the dependencies that you need to run the Python script. Third step is creating the Docker file, which basically specifies how anyone that has Docker installed could run your Python script. So for that, they need to have the requirements.txt file and then run python main.py. So that's what the Docker file specifies. And then basically you can start defining your cloud build.yaml file, which basically defines how we're gonna build our Docker image, and we're gonna push it to artifact registry. And then we're gonna execute that as a cloud run job. But I will also explain that in a bit. Maybe that's the next thing we can do, because in the meantime I see that we have created all the resources. So now, for example, if I go back to my instance, as you can see, the toys inventory database has been created, a artifact registry has been set up, which is called default repository, as you can see. So here we're going to be able to store our Docker image. So now if I would go back to that folder of initializing the database, we can actually now push that Docker to this repository on artifact registry, but that's probably also explained in the README over here. So this is an app that connects to the database as a super user and sets up the permissions and the PG vector extension. To build the images, change into each directory named above and run the following command. Note that for 2 project setup, that's not relevant for us because we don't have 2 separate project setup. So the only thing you then need to run from that folder is this. So I just need to run this gcloud build submit with your cloud build.yaml file. So as you can see, we're gonna run docker build and then basically push our Docker, this one over here, to artifact registry. Okay, and so the only thing I have to change here is the region. Europe West 1 is the one that we are using. So if I run that from this folder over here, it should just grant those privileges on the database. So as you can see, what is happening now is we're like cloud build, which is just a service that Google provides to make it easier to build and push Docker Docker images to artifact registry, is being executed at the moment. As you can see, it has successfully built your Docker image and it has tagged it, so you can also give a certain tag, certain identifier to your Docker image, and then as you can see, it seems to have pushed it. So if you go back now to artifact registry and I refresh this, yeah, it has created our Docker image with the tag latest. So that was also specified, I think, in the cloud builds. Here we specify the tag. So that's with this T flag you can specify the tag. So yeah, cloud build is just a service, like cloud build is a service that Google provides to easily build, test and deploy applications. So it just allows you to easily build your Docker container, or sorry, Docker image, and then push that to artifact registry. Yeah, I have to say image because it's not yet run as a container. Like a container is an actual executable thing that is running and serving requests or doing the actual work. Because now we have just pushed our Docker image to artifact registry, and then you can use Cloud Run to actually execute it. So that's maybe the next thing we can do. So deploy to Cloud Run and see it work. Deploy the init database as a Cloud Run job and let it run to completion. So yeah, now we have just like pushed it to artifact registry over here, and this just defines connecting to the database and granting the privileges, but it's not yet being executed. So that's the next thing we can do. Before we deploy anything, we need to update the Cloud Run YAML files to point to the images we built above. Right now, if you look into any of the job.yaml files, so if you move here to, oh sorry, I'm in the wrong folder. Yeah, I need to be in the Cloud Run folder, init database, job.yaml. This is then basically defining how the Docker image is gonna be executed as a Docker container on Cloud Run jobs. So Cloud Run jobs is just a service, again, a serverless service, so we don't need to provision any virtual machines ourselves to basically execute that. So maybe for easier visibility, I can show it here. So yeah, this is also a bit new for me, but this is basically defining, as you can see, we seem to specify a bunch of environment variables over here. Okay, here we probably need to change that image over here. So if I go here to the README again, before we deploy anything, we need to update the Cloud Run YAML files to point to the images we built above. Right now, if you look into any of the job.yaml files, you'll see that the image has the project and region strings, and we need to change this. Fortunately, we have a script to do this for us. For 2 project setups, the project should be... Okay, so apparently there's a scripts folder. Okay, that's over here, configure jobs. Nice. Okay, let's try to run that script. So I'm gonna go back to the run folder. Then here we have the scripts. So cd scripts. I assume that's how we need to run it. Okay, yeah, they just run it from the... So bash scripts configure jobs, and then here you need to also specify your project. So again, we need the project ID. So let me go back to the Cloud Console. So we need the project ID. And then we also need to specify the region. Europe West 1. Import comment not found. Syntax error. Okay, I'm just gonna ask this to Cursor. Can you please fix this? Yeah, Cursor is alongside Claude.ai my favorite tools, and in this case, as you can see, we're using Gemini 2.5 Pro. The error occurs because you are trying to execute a Python script using bash. Okay, yeah, maybe I didn't need to have the bash. I thought... Okay. Well, in the README they also say that you actually don't need bash. They say just run this. Let me try again. Okay. Okay, as you can see, it has updated our 3 files and it has filled in the image over here. Great. Nice. So now we can actually execute our Docker image as a container on Cloud Run jobs. So let me show that. So if I go, so the service we're going to use now, so maybe I have to close a bunch of tabs here because we have way too many. So as I said earlier, we pushed our image to artifact registry. So this is available now here. And now the service we're going to use is Cloud Run jobs. So this is a serverless service. So it allows you to just execute a Docker image as a container on Cloud Run in a very easy way. So, and the only thing you need to do for that, they probably also specified a comment for that, to not have to specify the cloud region, blah, blah, blah. Okay, here I specify how you can... First, we will deploy the init database job that connects to the database as the Postgres user, creates it, and grants permissions. create the cloud run job. Okay. gcloud run jobs replace. So this is going to create the job. So if you go back to our init database folder, failed to load. Oh yeah, I'm already in that folder. I can just do this. So this is going to create the job on Cloud Run Jobs. So this is going to basically create the job. So basically if we go here to our jobs, we're going to see it appear over here. Still running. Initializing project for the current region. So it's going to appear here. So we're first going to just create it, and then we can actually execute it. So then it's gonna run the Docker container and execute the initialization of the database. This takes some time. And then we can actually execute it using the gcloud run jobs execute command. And then we can move on to the two other jobs. So like once we have initialized the database and grant the permissions, we can move on to the second one, which is loading the embeddings. So as you can see, the setup is very identical. Again, you need to start by defining a Python script. So here what we're gonna do is, I think we're loading some CSV files, some toy data, just to show it for demo purposes. And then a PG vector, like this open source package that I talked about before, to create the vectors and then compute the vector similarities. We're gonna use PG vector for that. So here, as you can see, they use the register vector function. So they load the initial CSV file. They only load specific columns, 4 different columns. And then I think, they're gonna load that data into the SQL database. So here they create a table, they call it products. They specify the names of the columns along with the types. So we have 2 text columns and then a numeric column as well. And as you can see, the first column, the product ID, is used as the primary key. And then here the actual like turning the text into vectors is happening. So that's happening here. So here what is happening is chunking, and then each chunk will be turned into an embedding. So what do we mean by that? Well, basically when we are creating our vectors, like when we want to create a vector representation of all the text in that CSV file, we are going to use an embedding model. So for that, the one they are using in this tutorial over here is a text embedding API from Google Cloud. So Vertex AI provides, as you can see, different models for turning text, so just strings, into vectors. So a vector is just a long list of numbers that is not really human interpretable anymore, but can be used by computers to compute similarity between text and basically understand text in a better way. As you can see, they provide English models, multilingual models, and also a new experimental Gemini embedding model. We're not going to use that one. Let me see which one they use in this case. And that's happening over here. So they use the text embedding Gecko 003 model. This is this one, so it's an English model, so it seems that the text is English only. But it's already not the latest anymore, because there is now already text embedding 005. And so these embeddings, they take some text as an input. Maybe I can also create a nice visualization of this. So basically this is what's happening. Like, they take in some text and they produce these vectors, these long list of numbers that the computer can use to better represent the text. But these embedding models, like the Gecko 003 model, for example, they only can take in a certain amount of text. Like, you can just not just feed the whole book into an embedding model and get a single vector out. Well, some models might be able to do this, but the problem is that vector would then represent your whole book, which is not that useful, because you want to typically represent just small portions of text, also called chunks, with an embedding model, because each vector will then represent a specific section in your text, or a specific chapter, or a specific subject, specific topic. This is typically optimal if you want to then retrieve the most relevant chunks, because then we're gonna just use the vectors of each of the chunks, use the vector over query, over question, and then compute pairwise all the vector similarities between the vector of our question and the vector of each of the chunks, and find the most relevant portions, the most relevant chunks of our text. So the chunking, which is done over here, is just done because we want to not just feed long amounts of text to our embedding model. Rather, we create smaller portions. For that, they use the recursive character text splitter from LangChain. This is a popular chunker, so it allows you to split up your text into smaller pieces called chunks, and then we're gonna turn each chunk into one embedding vector. As you can see, you can also specify some hyperparameters over here, like the size of each chunk is in this case 500 characters, and they don't use any overlap, where you can definitely play around with these and get better results if you, for example, increase the chunk size or use an overlap. And then here they're actually gonna turn each chunk into an embedding using that Gecko model. So as you can see, we first are gonna chunk up our text, and then here we're gonna send batches of 5 text to the embedding API. Why 5? I've seen that in the documentation of Vertex AI text embeddings that you cannot specify more than 5 text at once to the model. As you can see, that's over here. You can get text embeddings for a snippet of text by using the Vertex AI API or the Vertex AI SDK for Python. For each request, you're limited to either 250 input texts in the US Central 1 region, but we're not using the one. In other regions, the max input text is 5. So this is why they use a batch size of 5 here. We can only send 5 texts or 5 chunks at a time to the embedding model. And they also use this retry with backoff mechanism over here, because sometimes you might get rate limited by the API, like you only have a certain amount of requests that is allowed per minute. You can of course ask for what is called a quota increase on at Google, so this allows you to get a higher rate limit, but by default it's probably not that high, so this is why they will retry with a certain backoff mechanism. And then we finally are gonna have our product embeddings, like all these embeddings of our individual chunks, and then we're gonna store them as a separate table in our SQL instance, so they call that the product embeddings table. And as you can see, it's then linked to our original table using this product ID primary key. Okay. And then, once you have your vectors created as a database, you also need to turn it into what is called an index. So an index is some kind of efficient representation of your vectors, of your embeddings. So this will allow you to very easily or very quickly, very efficiently compute these vector similarities. There's a very clever algorithm behind that, which I'll also have to leave for a different video. But the vector index is just a very efficient representation of all your vectors, such that you can do similarity search in a very fast way. Okay, I talked a little bit about this load embeddings Python script. I think in the meantime, our Cloud Run job must have been finished. So let me go back to our Cloud project. As you can see, our initialized init database job has been created, but as you can see, it has not been executed yet. So this is why we can now move on to the Cloud Run jobs execute. Okay. So now, we also apparently need to specify a region. So I'm gonna specify Europe West 1. So this is 17. And then it's gonna actually execute that. So we're gonna do the exact same thing for the second job, the load embeddings one. So we define it in a Python main.py script. We define our requirements. As you can see here are more requirements. We need LangChain. We need the Vertex AI SDK for accessing the embedding API. And then I assume they use the secret manager to access the API key. Or not, or don't we need an API key? Oh no, I think we are already, we can actually just authenticate using the default authentication of gcloud, so we don't actually need to specify an API key over here. We might need to do that when using the large language model. So as you can see, it has been executed. So if you go back here, and as you can see, yeah, we have successfully executed it. You can also view the logs over here. So it runs the job, it grants the privileges, and then it's done, and it exits the Docker container. So you can actually also see over here like that we're actually using that Docker image that we pushed to artifact registry. We also specified some environment variables. So these were defined, I think, in the job.yaml file. Yeah, these are the environment variables that we have to define, and so on. You can also specify like what are the resources that you need to run that job, like the amount of CPUs. In this case here, we only need 1 CPU and 2 GB memory, because it's just a very simple, lightweight job. So that was just initializing the database. So now we can move on to the next job, which is loading the embeddings. So this one, again, a Docker file is created, which is gonna, as you can see, we're gonna have to copy that CSV file over to our Docker image, and then we're gonna again execute it using Python main.py. So let me again create a Cloud Run job for that. So for that, yeah, we're gonna first build the image and we're gonna push it. So I have to move here back to the load embeddings folder, and then I can run the gcloud build submit command, specifying our different parameters like the region, as well as, okay, that's the only thing we have to specify. So I'm gonna do that. So again, what this command is gonna do is it's gonna use the Docker file. So here, the load embeddings, it's gonna use that Docker file, and based on this YAML file, it's gonna push that to artifact registry. So the nice thing about Docker containers is also like that if you come back 1 or 2 years later, yeah, your Docker container should still be able to be executed, because you have defined your requirements, you have defined the way to execute it. So you can come back like 1 or 2 years later and it will still be able to execute, which is pretty nice. So if you go back here to artifact registry, we move on to a repository here, there should appear, yeah, it's still, as you can see, installing the requirements in that Docker image. So that's basically done over here. That's this tab that is currently being run. And then the CSV file is actually just stored in this. No, we don't want any extensions to be installed in cursor. But so as you can see, like the way that we're gonna execute this whole load embeddings script is identical to the initialization of the database. So we're just gonna push the Docker image first to artifact registry, that's being pushed over here, and then we're gonna use that Docker image and execute it on Cloud Run jobs. So Cloud Run jobs is very handy if you want to just execute some Python code or some other code that you have. And maybe in the meantime, because I've already explained like how this load embeddings Python script works, let's then move on to the final app, which is the Chatbot API, a simple JSON API that supports natural language queries. So there, yeah, we're gonna have the G of RAG, so Retrieval Augmented Generation. The G stands for generation because we're gonna use an LLM, a large language model, to then also, like, it's gonna receive a certain natural language query, a certain question regarding that product database, and then we can just ask a question. We're gonna use the embedding model to turn our question into an embedding vector. Maybe let me explain that using ScallyDraw. So what is going to happen? Maybe they have some sample question that they're going to ask. Yeah, so for example here they ask what is a good day for rainy days. So that will be the question. So what is going to happen is we're going to first use our embedding model. So this is going to be embedding the question. So for that we're going to use the using the Gecko 003 model, because that's the same model that we use to embed all of our chunks. So that is gonna give us some vector. I'm just gonna make up some random numbers over here to represent that vector. It's just a long list of numbers. Okay, and then we can use that vector, that embedding that we created for a question, to look up within our database. So let me maybe use a nice icon for a database. So then we have here all of our chunks. So this is like our embedding table within Cloud SQL, which stores the embeddings of all the chunks in an efficient index. And so then we can basically do a pairwise lookup. So then we basically do a retrieval operation. So there, what we're gonna do is like compute pairwise vector similarity between the embedding of the question and each of the chunk embeddings. So that's happening over there, and then once we have done that, we basically get the most relevant questions. Sorry, the most relevant chunks. Like let's say we get the top 5 most relevant chunks that we retrieve from our database, and then we basically provide those to an LLM. So here we have a ChatGPT kind of model, so an LLM. And then what it's going to do is it's going to receive that question together with the most relevant chunks as an input. So it's going to get what is a good toy for rainy days together with the 5 most relevant chunks. Maybe for clarity, yeah, it's something like this. I don't want, yeah, this might be better. Okay, and then the ChatGPT model is hopefully gonna provide a nice answer. So then it's gonna, for example, say, what is a good toy for rainy days? It's going to say parapluie, for example. A parapluie might be a good fit. Just to illustrate. So this is the whole idea, of course, of RAG. This is what we call a RAG, or Retrieval Augmented Generation application. Alright. So that's the whole idea of this app. Okay, so as I said earlier, we have pushed the load embeddings app. Now, as you can see, so now we can execute it using Cloud Run Jobs. So let's go back here. That's what we have to do now. So now we have to create, I have to move back. So now we create the Cloud Run job, which again links, okay, that was pretty quick. So now if you move to Cloud Run Jobs, it has not been executed yet. You can actually also just click this button over here, but let's do it programmatically. And then again, we need to specify the region Europe West 1, which is 17. Now we're actually gonna chunk and load all the embeddings in our database. So that's basically what's being populated over here. And then so the final step is this Chatbot API. So here, this one, as you can see, has a bit of a different structure. I don't see a main.py script, as you can see, because here I think they're gonna create what is called a microservice. It's like a Flask or Fast API server. So what do we mean by that is basically an application programming interface or API. So it's basically going to be some kind of server to which people can send requests, and then your microservice, in this case called Chatbot API, is going to perform your request. In this case, it's going to perform this whole process of retrieving the most relevant documents for your question. It's going to embed the question, retrieve the most relevant documents, give the answer, and then it's going to send that as a response. So for that, Fast API is a popular option. So Fast API is also open source. It's a framework to build very easy microservices. I would say either use Fast API or Flask. Those are like the main frameworks people are using for creating a microservice in Python. So in this case, they use Fast API. So you will also see in the requirements.txt that Fast API is specified over here. So we can actually look into the main logic. So again, we are going to use that same embedding model because, as I said earlier, we're going to need that to embed our question. Like we're gonna embed the question that comes in. So I think we can see that over here. So as you can see, find by query. So find by query, what it's going to do is it's going to first embed the query. So our query is the question. Like the question is going to be embedded using the embeddings service. So the embedding service is this gecko 003 model. It's embedding that, and then here we do the vector lookup. So here we're going to do that retrieval step, like computing the pairwise vector similarity between the embedding of the query and each of the embeddings that we store in our database. So yeah, for that they are performing some SQL query with vector matches at. So as you can see, they use this vector similarity operator over here that we saw earlier in the README of PG vector. As you can see, so they use cosine distance to find the best matching vectors, and then they order them by similarity. And as you can see, they limit them by 3. So we are only going to retrieve here the top 3 most relevant chunks, and then we provide those to an LLM. So that's happening over here. And then here, as you can see, those best 3 matches are returned. So we're going to return the names of the product, description, and the price. Because in our case, like in this toy dataset, they use some product CSV file. So every row is a product. And then as you can see here, they also provide some prompt. So this is actually what is being also added over here. So we're not going to just feed the question and the 3 most relevant chunks, but also a certain custom prompt. And so on. So I'm going to add 3 dots here because this is not the full prompt. But so we're going to give our prompt together with the question and the most relevant chunks to our LLM. So that's happening over here. You will be given a detailed description. Yeah, there's even a type over here of different toy products enclosed in triple backticks and a question. Select one toy that is the most relevant to answer the question. Use that, select the toy description, answer the following question. So then, yeah, here we're gonna feed our question together with the most relevant retrieved chunks to the LLM. So in this case, yeah, we're not gonna use ChatGPT because, of course, ChatGPT is developed by OpenAI, and OpenAI models are only available on Azure, whereas Google provides the Gemini LLM. So in this case, let me see where they specify Gemini. They're not specifying it anywhere here. Let me find. Okay, so they use AI platform. Okay, we just that's actually pretty interesting. So if you just initialize Vertex AI without any arguments, I think it's just going to default to Gemini. Load summarized chain. Yeah, they also use LangChain, which is kind of an abstraction over the LLM APIs to then use the LLM. I'm personally not really using LangChain. I just prefer to use the large language model APIs right away. But then, yeah, basically the answer is going to be generated over here. And they also use, prompt template is a class within LangChain that you can use to like manage your prompts easily. So that's another thing you could use. And then finally, the LLM is going to generate an answer, which is then returned over here. So like this Fast API app, as you can see, they define a find by chatbot function over here, and this is then provided to the user as a chatbot endpoint. So they also provide a search endpoint. So this app that we built basically will have two endpoints, a search and a chatbot endpoint, and also a root. So, but that's the main logic. So it's basically deployed as a Fast API server. Again, we can turn it into a Docker image. We're gonna push that to artifact registry in the exact same way. So we have defined the requirements.txt. But as you can see here, the command is different. We're not just gonna run python main.py. In this case, we're gonna expose our Fast API server on a certain computer with a certain port. Like in this case, it's gonna be executed. It's gonna be run on a computer at port 80. And then again, we're gonna use cloud build to push the Docker image to artifact registry. And then I think again cloud run is going to be used, but in this case we're not going to use cloud run jobs. We're going to use just plain cloud run to then basically put that server on Google Cloud so that anyone can use it, as long as you're authenticated, of course. So in this case, as you can see, the load embeddings job is still executing. That's interesting. So it seems to take some time. And I also don't see any logs, which is weird. Maybe they don't have any logs, because actually we started this already nearly 10 minutes ago, but it seems to still perform the chunking and the embedding. But so the final step, maybe we can already do that, is we can push the Docker image over Chatbot API to artifact registry. So for that I can go to the Chatbot API folder, and there I can run this command. Again, I need to specify my region, Europe West 1. So let me go back to artifact. So we already have the two over here, and now it's going to also push the one for the Chatbot API that uses things like LangChain and so on to artifact registry. Okay, but so this one is still running. And then finally, once we have deployed our Cloud Run app, we can then actually just send a request to it. So then we can just send a question like, what is a good toy for rainy days? And then we should be able to get a response generated by the large language model, which is basically going to perform this whole RAG, Retrieval Augmented Generation setup for us. So yeah, I'm just going to wait here until the load embeddings job is finished, and then I will come back. Alright, so we're back. Eventually, as you can see, I had to debug this load embeddings job on Cloud Run jobs quite a bit, because initially it just didn't work, like it just hang. And when looking in the logs, yeah, initially it was just terminating because it had reached the maximum default timeout of Cloud Run jobs, which is 600 seconds or 10 minutes. So that was weird. Like, I didn't change anything to the code. Then I just tried it again, but I expanded the timeout to an hour, but even that didn't help anything. So then I had to debug this a bit. So then I had to go into the load embeddings step. So I looked into this main.py script and I went over all the code. But everything, seemed fine. Here, for example, the connection was made with the Cloud SQL database, but for some reason I didn't see any print statements. Like, for example, when I checked the logs, for example, this was just not shown, so that was weird. So then I asked Cursor to debug that, and then you can apparently add flush equals true to print statements. So if you check here the code, within my Cloud Run, I added flush equals true to all the print statements because this is run asynchronously, and apparently then you need to add flush equals true to see these actual print statements. So that allowed me to basically debug the application in an easier way. So I added flush equals true to basically all the print statements, and then I saw that it actually hang in this step, generate the vector embeddings, because there what is done is, so we are using the the Vertex AI embeddings API, and we call that API with a backoff, an exponential backoff, but I didn't see this being printed, so that was weird. And then eventually I found the error. It had to do with the fact that the text embedding model, which this repository uses by default, is the Gecko 003 at 003 model, but that one is actually deprecated, or Google at least does not recommend to use that model anymore. So here in the guide they say that, for example, text embedding Gecko 001 and 002 are already deprecated and they will no longer be accessible. And then Gecko 003 is also deprecated. So what I did was I just replaced it by the latest model, which is the text embedding 005 model. So note that if you do that, all the chunks will be embedded using this newer embedding model, which also means that we had to update the Chatbot API, which is then gonna embed the question and then perform pairwise vector similarity to find the most relevant chunks. So also there I changed the embedding model to use text embedding 005. And when I did that, I basically just redeployed it to, I basically pushed a new Docker image to artifact registry. So I again follow the README here. So I went into this step over here, gcloud build submit. So just pushing a new a new Docker image to artifact registry, and then I redeployed my job, and then I execute it using the gcloud run jobs execute command. And now, as you can see in the logs of the Cloud Run job, everything was done correctly. Like here in the logs, everything was embedded correctly, so it's also printing, for example, the first few rows and then also the actual embeddings, and finally it creates the index. Alright, and then the final step, once we have populated the database with all the product descriptions and their embeddings, it's time to then deploy the Chatbot API microservice, which is the Flask app. So also there I followed the steps. So the first thing you have to do is also push a Docker image for your Flask API or Flask app. So here the Docker file is being defined to expose a web server. So for that I also run the gcloud build submit command. So this one pushes one to artifact registry. So you can see that over here. In the default repository we have one for the Chatbot API, and then once you have done that, you can also deploy it to Cloud Run. But so note that now we're going to deploy it to just default Cloud Run and not Cloud Run jobs, because it's a web server that listens to requests, which is different from a job that is just executed once or on schedule. So if you go here to Cloud Run, you will see, so there's a distinction here between services, which are like web servers kind of things. Flask or Fast API is typically used for that, and then the jobs, which we use to initialize the database and then load all the embeddings into it. So here, as you can see, I deployed it, and also here you can check the logs. And yeah, initially I also saw some error happening here, and again, it had to do with the fact that the model that was being used was outdated. So within the Chatbot API, they use a large language model here in the main.py script. They initialize the LLM here just with the Vertex AI class from LangChain. But the problem was that that was defaulting to a model that was already outdated. It was like called Text Bison 1.1 or something like that, which is like an older LLM developed by Google. So what I did was I also replaced the LLM. So if you go into the Chatbot API, I replaced that by the Gemini 2.0 Flash model, which is currently one of the models. Like if you search for using Gemini on Vertex AI, they do recommend using the Gemini 2.0 Flash model. And so that's what I did. And then I redeployed it again on, so I pushed another Docker image to artifact registry, and then I redeployed my Chatbot API service. So again, after you create a new Docker image, you need to run, well in this case you need to run a different command. So as you can see here, you need to run gcloud run services replace Chatbot API service.yaml, and that's gonna refer then to this file, which basically defines, it also passes some environment variables, like to connect to the Cloud SQL database, because everything is run within that virtual network, that VPC. And then eventually you end up with your service, and then you can check the logs, and then it's finally time to test it out. So what you can do then is port forwarding. So by port forwarding, we basically mean that we're gonna run the service on our own computer on localhost, as if it's running on Google Cloud. So you can actually run this command. Let me do that. So if you do that, what is basically happening is, it's proxying, so it's basically pretending that it's that remote Cloud Run service. So your own computer is then basically running, taking requests, which is it then gonna send to Cloud Run, but it's running locally at localhost port 8080. So if you then in Fast API, you can always do /docs to see like the spec of the API that you built. So remember that we had 2 endpoints, well actually 3. We also have a root and then search and chatbot. So that's defined if you go into the app main.py file. So we have the 3 endpoints defined over here. And the one we're mostly interested in is the chatbot one, because there we can ask questions. And so Fast API's docs page also allows you to directly try it out. So that's what I did over here. And then you can just ask a question like, what is a good toy for rainy days? And then click execute. And so now you can actually see or check the logs on Cloud Run. So here for now I don't see anything except that we want to access the docs. But if you refresh, or maybe there are no logs being shown, because as you can see, you get an answer, which is great. The step 2, Paw Patrol Lookout Tower water table would be a good toy for rainy days. So now we have basically performed the whole RAG setup. So we have retrieved the most relevant documents or products in this case from the CSV file, and then sent those to Gemini 2.0 Flash. So maybe you can also quickly check the data, because I'm curious whether this response makes any sense. So remember the data set is defined there. So I'm gonna create a new notebook, say import pandas as PD, and then read the CSV file. So for that, I'm gonna pass the path to that. So let me run this. Need to install a bunch of things. I probably need to install. What I could do maybe is just run it for now in a terminal. if we have pandas installed. No, we don't. So I'm gonna activate my virtual environment. In the meantime, I created a Python virtual environment. It's very easy to do, just python-m-v-e-n-v. Okay, so we have created it. So now I can okay, now I'm gonna open up my CSV file, print the head. So what we basically have for each product is a certain identifier. Yeah, wait, we have different columns. Product URL, product name, description, package size, category, postal code, and available. And I remember when we were pushing everything to our database, we only kept, I think, 4 columns. The name of the product, the description. So let me maybe do that as well. So let me maybe see the first row. Yeah, basically I think based on the description of the product, it tries to find the best match. In this case, as you mentioned, rainy days, it tries to match a product which probably, yeah, mentions things like indoor, so that you can use it for indoor purposes. So yeah, I think that's it. So we have basically explained how you can, yeah, deploy a production-ready application, a generative AI application. I wouldn't say in less than 30 minutes, because we had to debug some things like making sure that we are using the latest models, that everything is running fine within that virtual private network. But eventually we end up with a Chatbot API. So this could then, for example, you could build a front end on top of that, so that people can just enter their message in the in the chat box, and then yeah, the fact that Cloud Run here also supports things like auto scaling. So that's, I think, a big feature of Cloud Run. So like if your API would then get a lot of requests from all kinds of users all around the world, Cloud Run will just take care of scaling automatically for you. So I think, yeah, by default it scales automatically. I think it also has scale to 0, which means that it can also scale down just to 0 instances in case nobody is using your app, which is quite nice. And so, yeah, I would say Cloud Run, so the serverless service to deploy a Flask or a Fast API app, is quite handy if you want to put that in production. And then the jobs themselves are quite handy if you want to just run a Python script or some other piece of code just once or on a scheduled basis. Because another thing that people often do, especially if they have a RAG app in production, is typically you have new data that comes in, let's say every day or every week. So that also needs to be ingested into your database, into your vector database. So then you could set up a Cloud Run job that automatically takes in new data as it comes in. For that, for example, another service which could be interesting on Google Cloud is PubSub. So publish, subscribe. So there your Cloud Run job could basically subscribe to a topic, what is called on PubSub. So then basically whenever someone pushes new product descriptions, for example, in this case, to this PubSub service, then your Cloud Run job could subscribe to it. And then every time new messages are being put into that topic, then your Cloud Run job could be run. So it can basically automatically chunk and embed new descriptions as they come in, and in this way your vector database gets updated on a regular basis. But that might be for a different video. In this video I just wanted to explain the main setup if you want to deploy such a generative AI app on Google Cloud. And as I said earlier, there's also the more low-level solution where you deploy everything on Google Kubernetes engine. But I think especially for beginners it might be more useful to start looking into Cloud Run, because it makes it more easy than compared to the lower level solution of Google Kubernetes Engine. So I hope you found this video useful, and yeah, for me, I would also say that this is mostly the way that I deploy generative AI apps on the cloud. Of course, there are more things involved in it. Like, for example, I'm not using CloudSQL myself as vector databases. I have experience with other vector databases like Weaviate and Elasticsearch, but I'm definitely interested in exploring more the use of CloudSQL, like a Postgres database for generative AI apps as well. So I might make other videos on that in the future as well. But yeah, I would say the main setup, especially also the fact that you're running everything in a virtual private network, makes it quite a robust solution. So yeah, I hope you find this video useful, and see you in the next one. Bye-bye. A final note that I want to add here to this video is that we received a report of the cost of this jumpstart that Google provides on deploying this GenAI app on GCP. And as it turns out, you can see that the cost of CloudSQL is pretty high, especially if you compare it relatively to all the other services that we used for this particular project. So even just for a few days, I saw that we were paying nearly 300 euros for the CloudSQL Postgres instance, which is of course quite a lot. Other than that, you can see all the other costs are relatively marginal, because Cloud Run is a serverless service, so it only spins up when there's demand. Otherwise, you don't need to pay for anything. And other things like artifact registry, the DNS server, Gemini, and the embedding model, as you can see, yeah, we barely use those. So it's quite interesting here to see that this costs so much. So yeah, I was then interested also in seeing like the pricing of the CloudSQL instance. So yeah, there's a pricing page that Google provides, but it also depends on the amount of CPUs you use for the instance, the amount of memory you provide. So what I did was I went back to the Terraform configuration and then to the database, and there we can see, so they are making a CloudSQL database instance with, for example, 250 gigabytes of disk space and 8 CPUs and so on. So I just asked it to Claude, like, how much do you estimate a CloudSQL instance like this would cost? But yeah, apparently it's also the Enterprise Plus edition and so on. So we're definitely almost certainly not using the cheapest instance for this, but Claude estimates that the monthly cost would be around $2,000 per month. So that's of course quite a lot. But this also lines up a bit with my experience with developing RAG projects for clients, where the vector database is always the most expensive thing. It's not really the embedding models or the LLM APIs, which are already pretty cheap. It's not Cloud Run or artifact registry. It's typically the vector database, where you typically need to pay per hour that the virtual machine is running, or you need to pay for the size of the index that you're hosting. So yeah, this is definitely something to keep in mind, and I might make a different video on like comparing the different vector database solutions besides CloudSQL, because there are so many others available. There is, for example, there's Chroma, which is a popular and apparently also open source vector database. There's Elasticsearch, of course, which is used by a lot of companies, which is also providing the more traditional keyword-based search. Well, actually, most of the vector database vendors are offering that. And then there's also Quadrant. There is also well, you also have actually the vector databases on each cloud individually. So on Google Cloud, for example, you have Vertex AI Vector Search, which is the default vector database that Google provides. And I saw that they recently also added support for hybrid search, so the combination of keyword search and vector search, which typically results in better performance. So this would be another option, but also there I saw it can become very expensive, especially if you scale up the size of the amount of embeddings you have. So then it's important to reduce the dimensionality of your embeddings. For example, not using embeddings of size 768, but instead using a size of, for example, 256. And then you can also do things like quantization, which also significantly reduce the size of your embeddings. Then on Azure, you have something similar, which is Azure AI Search, which is also something that I've used in the past, which worked quite well out of the box. But again, it was the most expensive service for the vector database. And then another popular option is Weaviate, which is also open source, which also supports hybrid search and things like that. And you can self-host it on Google Cloud, for example. So yeah, this was just something that I want to add here as a remark, that vector databases are often the most expensive cost for RAG applications. So see you in the next video. Bye-bye.